In recent years, the field of natural language processing, NLP, has witnessed a remarkable transformation, driven by the emergence of large language models, LLMs. This course explores the foundations, applications, and societal implications of LLMs, as well as the challenges and opportunities they present. LLMs, such as the Generative Pre-trained Transformer (GPT) series by OpenAI and BERT by Google, represent a paradigm shift in NLP. These models, equipped with billions or even trillions of parameters, are capable of understanding, generating, and processing human language at an unprecedented scale. The introduction of the transformer architecture, with its self-attention mechanism, has played a pivotal role in enabling the success of LLMs. This architecture allows the models to capture long-range dependencies and contextual information efficiently, leading to breakthroughs in various NLP tasks. The significance of LLMs extends across diverse domains, from text generation and translation to question answering and chatbots. In text generation, LLMs excel at producing coherent and contextually relevant text based on a given prompt, powering applications such as auto-completion features, dialogue systems, and creative writing tools. In language translation, LLMs have revolutionized machine translation by achieving state-of-the-art performance and enabling zero-shot and few-shot translation capabilities. Additionally, LLMs play a crucial role in question-answering tasks, where they extract and generate accurate responses from textual data, contributing to advancements in information retrieval and knowledge dissemination. However, alongside their immense potential, LLMs also raise significant societal impact and ethical considerations. Bias and fairness issues in LLMs have garnered attention, as models trained on biased datasets can perpetuate and amplify existing societal biases, leading to inequitable outcomes. Addressing bias and promoting fairness in LLMs require careful data curation, model development, and evaluation processes. Moreover, concerns about misinformation and disinformation propagated by LLMs highlight the importance of developing robust detection mechanisms and fostering media literacy among users to combat the spread of false information. Privacy concerns are another area of ethical consideration, as LLMs trained on large-scale datasets may inadvertently capture sensitive information, posing risks to user privacy and security. Establishing ethical guidelines and regulations governing the development and deployment of LLMs is essential to ensure responsible AI practices and safeguard user rights and interests. Transparency and accountability are crucial principles in this regard, as they promote trust and understanding in AI systems by providing insights into model behavior and decision-making processes. Looking ahead, the future of LLMs holds promise and challenges. Advances in LLM research aim to scale models to even larger sizes while improving computational efficiency, enabling applications in multimodal understanding and lifelong learning. However, addressing open challenges such as bias mitigation, model robustness, and environmental sustainability requires concerted efforts from researchers, practitioners, policymakers, and industry stakeholders. Collaboration and knowledge sharing are key to advancing the field responsibly and ethically. In conclusion, large language models represent a transformative advancement in natural language processing, with far-reaching implications for society. By harnessing the power of LLMs while addressing their ethical and societal implications, we can unlock their full potential to enhance communication, enable access to information, and drive innovation across domains. As we navigate the complexities of deploying LLMs responsibly, it is imperative to uphold principles of fairness, transparency, and accountability to ensure that these technologies benefit humanity as a whole. Introduction to large language models. Definition and significance. Definition: large language models, LLMs, are sophisticated artificial intelligence models capable of understanding, generating, and processing human language at scale. These models are typically trained on vast amounts of text data, enabling them to learn complex linguistic patterns and structures. Significance: LLMs have revolutionized natural language processing, NLP tasks by achieving state-of-the-art performance across various applications, including text generation, translation, question answering, and sentiment analysis. They play a crucial role in advancing human-computer interaction, powering virtual assistants, chatbots, and language-based applications. LLMs have profound implications for industries such as healthcare, finance, education, and entertainment, where language understanding and generation are essential. Historical overview. Early language models. Early language models, such as n-gram models and hidden Markov models, HMs, laid the foundation for statistical language modeling. These models had limitations in capturing long-range dependencies and contextual information in language. Transformer architecture. The transformer architecture, introduced in the paper Attention is All You Need by Vaswani et al. 2017, revolutionized language modeling. Transformers utilize self-attention mechanisms to capture global dependencies and context, enabling efficient parallelization and scalability. Emergence of large language models. Breakthroughs in hardware capabilities, data availability, and algorithmic advancements led to the development of large-scale language models such as GPT, Generative Pre-trained Transformer Series by OpenAI and BERT, Bidirectional Encoder Representations from Transformers, by Google. These models, with billions or even trillions of parameters, have significantly improved the quality and performance of language understanding and generation tasks. Recent developments. Recent advancements in LLM research focus on improving model efficiency, interpretability, and robustness. Techniques such as model distillation, sparse attention mechanisms, and ethical considerations are gaining attention in the LLM community. Impact on society. While LLMs offer tremendous potential, they also raise concerns about biases, misinformation, privacy, and ethical use. Understanding the societal impact of LLMs is crucial for responsible deployment and regulation in various domains. Fundamentals of language modeling. Basics of natural language processing. Definition of natural language processing, NLP. Natural language processing, NLP, is a branch of artificial intelligence, AI, that focuses on enabling computers to understand, interpret, and generate human language in a way that is both meaningful and contextually appropriate. Key concepts in NLP. Tokenization, breaking down text into smaller units such as words or subwords. Part-of-speech tagging, assigning grammatical tags to words, e.g., noun, verb, adjective. Named entity recognition, NER, identifying and categorizing named entities, e.g., person names, locations, organizations in text. Syntax and parsing, analyzing the grammatical structure of sentences to understand relationships between words. Semantic analysis, extracting the meaning from text, including word sense disambiguation and semantic role labeling. Discourse analysis, understanding the structure and coherence of larger units of text, such as paragraphs or documents. Statistical language modeling. Definition of language modeling. Language modeling is the task of predicting the next word, or sequence of words, in a given context. It captures the probability distribution over sequences of words in a language. Statistical language models. Statistical language models estimate the probability of a word sequence using statistical techniques. N-gram models are a simple type of statistical language model that calculates the probability of the next word based on the preceding N1 words. Limitations of N-gram models include the inability to capture long-range dependencies and the sparsity of training data for high-order N-grams. Challenges in language modeling. Out-of-vocabulary words, handling words not seen during training. Data sparsity, dealing with rare or unseen word combinations. Long-term dependencies, capturing dependencies between distant words in a sequence. Evaluation metrics for language models. Perplexity, a measure of how well a language model predicts a sample of text. Lower perplexity indicates better performance. Word error rate, where the percentage of words in a recognized transcript that differ from the referenced transcript. Recent advances. Neural language models, neural network-based language models, such as recurrent neural networks, RNNs, and transformers, have achieved state-of-the-art performance by capturing complex linguistic patterns and contextual information. Architecture of large language models. Transformer architecture. Introduction to transformers. Transformers are a type of deep learning architecture introduced in the paper Attention is All You Need by Vaswani et al. 2017. They have become the backbone of many state-of-the-art models in natural language processing, including large language models, LLMs, like GPT and BERT. Key components of transformers. self-attention mechanism, allows the model to weigh the importance of different words in a sequence when processing each word, enabling capturing long-range dependencies. Multi-head attention utilizes multiple attention mechanisms in parallel to capture different aspects of the input sequence. Positional encoding provides positional information to the model, enabling it to understand the order of words in a sequence. Feed-forward neural networks process the output of the attention mechanism to generate the final representations of words or tokens. Encoder-decoder architecture. Transformers typically employ an encoder-decoder architecture for tasks like machine translation and text generation. The encoder processes the input sequence, while the decoder generates the output sequence based on the encoder's representations. The encoder and decoder consist of multiple layers of self-attention and feed-forward neural networks. Benefits of transformers. Parallelization. Transformers can process input sequences in parallel, making them highly efficient and scalable. Capturing long-term dependencies. The self-attention mechanism allows transformers to capture dependencies between distant words in a sequence, addressing one of the limitations of recurrent neural networks, RNNs. Flexibility. Transformers can handle variable length input sequences and generate variable length output sequences, making them suitable for a wide range of tasks in NLP. Self-attention mechanism. Overview of self-attention. Self-attention is a mechanism that allows a model to weigh the importance of different words in a sequence when processing each word. It computes a weighted sum of the embeddings of all words in the sequence, where the weights are determined dynamically based on the similarity between words. Components of self-attention. Query, key, and value. In self-attention, each word in the sequence is associated with three vectors: a query vector, a key vector, and a value vector. Attention scores. The similarity between a query vector and key vectors determines attention scores, which represent the importance of each word in the sequence. Weighted sum. The attention scores are used to compute a weighted sum of the value vectors, resulting in the attended representation for each word. Multi-head attention. Multi-head attention extends the self-attention mechanism by performing multiple attention operations in parallel. It allows the model to attend to different parts of the input sequence simultaneously, capturing different aspects of the context. Encoder-decoder architecture. Role of encoder and decoder. In an encoder-decoder architecture, the encoder processes the input sequence and generates a fixed-length representation, context vector, of the input. The decoder takes this context vector as input and generates the output sequence step by step. Sequence-to-sequence modeling. Encoder-decoder architectures are commonly used for sequence-to-sequence tasks such as machine translation and text summarization. The encoder processes the input sequence, e.g., source language sentence, while the decoder generates the output sequence, e.g., target language translation. Transformer-based encoder-decoder. Transformers have been successfully applied to sequence-to-sequence tasks by adopting the encoder-decoder architecture. Both the encoder and decoder consist of multiple layers of self-attention and feed-forward neural networks, enabling the model to capture complex relationships and dependencies between input and output sequences. Training large language models. Data preprocessing. Data cleaning and tokenization. Data preprocessing involves cleaning and formatting raw text data before training. Common preprocessing steps include removing special characters, lowercasing text, and tokenizing sentences into words or subwords. Vocabulary construction. Constructing a vocabulary involves mapping words or subwords to unique numerical identifiers, IDs. Rare or out-of-vocabulary words may be replaced with a special token during preprocessing. Batching and padding. To improve training efficiency, data is organized into batches, where each batch contains multiple input-output pairs. Input sequences within a batch are padded to ensure uniform length, typically with a special padding token. Model training techniques. Objective function. Large language models, LLMs, are typically trained using maximum likelihood estimation, MLE, where the goal is to maximize the likelihood of generating the next word in a sequence given the previous context. Gradient descent optimization. Optimization algorithms such as stochastic gradient descent, SGD, or its variants, e.g., ADAM, RMS-prop, are used to update the model parameters based on the gradient of the loss function with respect to the parameters. Learning rate scheduling. Learning rate scheduling involves adjusting the learning rate during training to improve convergence and stability. Common scheduling strategies include exponential decay, warm-up schedules, and cosine annealing. Regularization techniques. Regularization methods, such as dropout and weight decay, are applied to prevent overfitting and improve generalization performance. Dropout randomly masks out a fraction of input or hidden units during training, while weight decay penalizes large parameter values. Fine-tuning and transfer learning. Fine-tuning pre-trained models. Fine-tuning involves initializing the model with pre-trained weights and then further training it on a task-specific dataset. Fine-tuning allows leveraging knowledge learned from pre-training to improve performance on downstream tasks with limited labeled data. Transfer learning strategies. Transfer learning strategies for LLMs include feature extraction, where the pre-trained model's embeddings are used as input features for downstream tasks, and fine-tuning, where the entire model is fine-tuned on task-specific data. Benefits of fine-tuning. Fine-tuning pre-trained LLMs often requires less computational resources and training time compared to training from scratch. It enables leveraging large-scale pre-trained models trained on diverse data sources, leading to improved generalization performance. Challenges in fine-tuning. Choosing the right pre-trained model and fine-tuning strategy depends on factors such as the similarity of the pre-trained model's domain to the target task and the availability of labeled data. Evaluation of large language models. Metrics for evaluating language models. Perplexity. Perplexity is a widely used metric for evaluating the performance of language models. It measures how well a language model predicts a sample of text by calculating the inverse probability of the test set, normalized by the number of words. Lower perplexity values indicate better performance, as the model is more confident in its predictions. Word error rate, WER. WER is commonly used in automatic speech recognition, ASR, and machine translation tasks. It measures the percentage of words in a recognized transcript that differ from the reference transcript. Lower WER values indicate better accuracy in generating the target sequence. BLEU score, bilingual evaluation understudy. BLEU is a metric often used for evaluating the quality of machine translation outputs. It compares the n-gram overlap between the generated translation and one or more reference translations. Higher BLEU scores indicate better agreement with human-generated translations. Rouge score, recall-oriented understudy for gisting evaluation. Rouge is a set of metrics used for evaluating the quality of text summaries. It measures the overlap between the generated summary and one or more reference summaries based on n-gram co-occurrence and sequence similarity. Higher Rouge scores indicate better summarization performance. Human evaluation. Human evaluation involves assessing the quality of language model outputs through subjective judgments by human annotators. It can provide valuable insights into aspects of language generation, such as fluency, coherence, and relevance, that may not be captured by automated metrics. Benchmark datasets and tasks. Common benchmark datasets. Common benchmark datasets for evaluating large language models, LLMs include PenTreeBank, a dataset consisting of parsed Wall Street Journal articles for tasks such as language modeling and part-of-speech tagging. Wikitext, a collection of English Wikipedia articles used for language modeling tasks. GLUE, General Language Understanding Evaluation, a benchmark dataset for evaluating natural language understanding models across various tasks, including sentiment analysis, text classification, and question answering. SQUAD, Stanford Question Answering Dataset, a dataset for evaluating question answering systems by providing context paragraphs and associated questions. Evaluation tasks. Language models are evaluated on a variety of tasks, including language modeling, predicting the next word in a sequence given the previous context. Text generation, generating coherent and contextually relevant text based on a given prompt. Machine translation, translating text from one language to another while preserving meaning and fluency. Question answering, providing accurate answers to questions based on a given context. Text classification, assigning predefined labels or categories to text documents based on their content. Challenges in evaluation. Evaluation of language models can be challenging due to the subjective nature of language understanding and generation. Automated metrics may not always align with human judgments, leading to discrepancies in model performance evaluation. It's essential to carefully select evaluation metrics and datasets that are representative of the target domain and task to ensure reliable model assessment. Applications of large language models: text generation, text completion, and auto-completion. Large language models, LLMs, can generate coherent and contextually relevant text based on a given prompt or input. Text completion involves predicting the next word or sequence of words to complete a sentence or phrase. Auto-completion features in applications like word processors and messaging platforms leverage LLMs to suggest relevant word or phrase completions as users type. Dialogue systems and chatbots. LLMs power conversational agents and chatbots capable of engaging in human-like dialogue. Dialogue systems use context-aware generation to produce responses that maintain coherence and relevance within the conversation. Applications include customer service chatbots, virtual assistants, and interactive storytelling platforms. Creative writing and content generation. LLMs can aid in creative writing tasks such as generating poetry, stories, and song lyrics. Writers and content creators use LLMs to overcome writer's block, explore new ideas, and generate content for various media platforms. Language translation. Neural machine translation. Large language models have significantly advanced the field of machine translation through neural network-based approaches. Neural machine translation (NMT) models, based on LLMs, achieve state-of-the-art performance by capturing complex linguistic patterns and context. Zero-shot and few-shot translation. LLMs enable zero-shot and few-shot translation, where models can translate between language pairs not seen during training or with limited training examples. This capability is particularly valuable for translating between low-resource languages and adapting to new language pairs with minimal supervision. Domain adaptation and specialized translation. LLMs can be fine-tuned for specialized domains such as medical, legal, or technical translation. Domain-specific vocabulary and terminology can be incorporated into the model through fine-tuning, improving translation quality for specific domains. Question answering. Reading comprehension and QA systems. Large language models excel at question answering tasks by understanding and extracting relevant information from text passages. Reading comprehension tasks involve answering questions based on a given passage, while open domain QA systems can provide answers to a wide range of questions using external knowledge sources. Fact verification and knowledge retrieval. LLMs can verify factual claims by extracting and validating information from text sources. Knowledge retrieval systems leverage LLMs to search and retrieve relevant information from large text corpora, databases, and knowledge graphs. Chatbots and virtual assistants. Conversational AI. LLMs power chatbots and virtual assistants capable of engaging in natural and contextually relevant conversations. These AI systems assist users with tasks such as scheduling appointments, providing information, and assisting with customer support queries. Personalization and context awareness. LLM-based chatbots and virtual assistants can personalize interactions based on user preferences, history, and context. They adapt responses and recommendations to the user's language style, preferences, and previous interactions, enhancing user experience and engagement. Applications across industries. Chatbots and virtual assistants find applications across various industries, including e-commerce, healthcare, finance, and education, improving efficiency and accessibility of services. Societal impact and ethical considerations. Bias and fairness issues. Bias in training data. Large language models, LLMs, trained on biased datasets can perpetuate and amplify existing societal biases present in the data. Biases related to gender, race, ethnicity, religion, and socioeconomic status may manifest in language generation and decision-making processes. Fairness and equity. LLMs can impact fairness and equity in various domains, including hiring, lending, and criminal justice, by influencing decision-making processes and outcomes. Biased language generation by LLMs may contribute to discriminatory practices and reinforce systemic inequalities. Mitigation strategies. Mitigating bias and promoting fairness in LLMs requires careful consideration of data collection, model training, and evaluation processes. Techniques such as bias detection, debiasing algorithms, and fairness-aware training can help identify and mitigate biases in LLMs. Misinformation and disinformation. Spread of misinformation. LLMs can inadvertently propagate misinformation and disinformation by generating false or misleading content. Malicious actors may exploit LLMs to generate fake news, misinformation campaigns, and propaganda, leading to social unrest and undermining trust in information sources. Detecting and combating misinformation. Detecting and combating misinformation generated by LLMs is challenging due to the rapid generation and dissemination of content. Strategies include developing automated detection systems, promoting media literacy, and fostering critical thinking skills among users. Privacy concerns. Data privacy and security. LLMs trained on large-scale datasets may inadvertently capture sensitive information, posing risks to user privacy and security. Models may inadvertently memorize personal data, conversations, or behavior patterns from training data, raising concerns about data privacy and potential misuse. Ethical use and regulation. Ensuring ethical use of LLMs requires establishing guidelines, regulations, and ethical frameworks governing their development, deployment, and use. Stakeholders, including researchers, developers, policymakers, and the public, must collaborate to address ethical challenges and safeguard user rights and interests. Transparency and accountability. Transparency in LLM development and deployment is essential for building trust and accountability. Providing transparency reports, disclosing model biases, and implementing mechanisms for user consent and control can enhance transparency and accountability in LLM applications. Hands-on projects and exercises. Building a language model using pre-trained models. Project overview. In this hands-on project, students will learn how to build a language model using pre-trained models such as GPT or BERT. They will fine-tune the pre-trained model on a specific dataset or task to customize its behavior for their application. Steps involved. Select pre-trained model. Choose a pre-trained language model suitable for the task. Consider factors such as model size, domain relevance, and availability of pre-trained weights. Data preparation. Pre-process and prepare the training data for fine-tuning. This may involve tokenization, data augmentation, and splitting into training, validation, and test sets. Model fine-tuning. Fine-tune the selected pre-trained model on the task-specific dataset using techniques such as transfer learning. Training and evaluation. Train the fine-tuned model on the training data and evaluate its performance on the validation set using appropriate metrics. Hyperparameter tuning. Experiment with different hyperparameters, e.g., learning rate, batch size, to optimize model performance. Testing and deployment. Test the fine-tuned model on the held-out test set to assess its generalization performance. Deploy the model in a real-world application if applicable. Exercises. Experiment with different pre-trained models and compare their performance on the task. Explore the impact of hyperparameters on model performance by conducting sensitivity analysis. Extend the project by incorporating additional data sources or fine-tuning strategies to further improve model performance. Fine-tuning a model for a specific task. Project overview. In this hands-on project, students will fine-tune a pre-trained language model for a specific natural language processing (NLP) task, such as sentiment analysis or named entity recognition. They will customize the pre-trained model to adapt it to the task's requirements and evaluate its performance on a benchmark dataset. Steps involved. Task definition. Choose a specific NLP task to focus on, such as sentiment analysis, text classification, or question answering. Select pre-trained model. Select a pre-trained language model suitable for the task based on its architecture, performance, and compatibility with the task. Data preparation. Prepare the task-specific dataset for fine-tuning, including data cleaning, tokenization, and splitting into training, validation, and test sets. Model configuration. Configure the pre-trained model for the target task by adding task-specific layers or modifying the model architecture if necessary. Fine-tuning. Fine-tune the pre-trained model on the task-specific dataset using transfer learning techniques. Training and evaluation. Train the fine-tuned model on the training data and evaluate its performance on the validation set using appropriate evaluation metrics. Hyperparameter tuning. Experiment with different hyperparameters to optimize model performance and generalization. Testing and deployment. Test the fine-tuned model on the held-out test set to assess its performance and deploy it in a real-world application if applicable. Exercises. Experiment with different pre-trained models and compare their performance on the task. Explore the impact of fine-tuning strategies, e.g., freezing versus updating pre-trained layers, on model performance. Extend the project by incorporating advanced techniques such as multitask learning or domain adaptation to improve model performance on the target task. Additional resources. Provide access to code repositories, tutorials, and documentation for implementing fine-tuning techniques using popular deep learning frameworks such as TensorFlow or PyTorch. Future directions and challenges. Advances in LLM research. Model scale and efficiency. Future research in large language models, LLMs, aims to scale models to even larger sizes while improving computational efficiency. Techniques such as model distillation, sparse attention mechanisms, and parameter pruning can reduce the computational cost of training and inference without sacrificing performance. Multimodal and multilingual LLMs. Multimodal LLMs integrate text with other modalities such as images, audio, and video to enable more comprehensive understanding and generation of content. Multilingual LLMs can process and generate text in multiple languages, facilitating cross-lingual applications and improving accessibility to language technologies. Continual learning and lifelong learning. Continual learning techniques enable LLMs to adapt and learn incrementally from new data and experiences over time. Lifelong learning approaches allow LLMs to accumulate knowledge and skills across multiple tasks and domains, leading to more versatile and adaptive AI systems. Open challenges and opportunities. Ethical considerations and responsible AI. Addressing ethical challenges related to bias, fairness, privacy, and transparency remains a critical area of research and development in LLMs. Building ethical and responsible AI systems requires interdisciplinary collaboration, stakeholder engagement, and regulatory frameworks to ensure equitable and accountable deployment. Robustness and generalization. Improving the robustness and generalization capabilities of LLMs is an ongoing challenge, especially in handling noisy or adversarial inputs and out-of-distribution data. Techniques such as robust optimization, adversarial training, and domain adaptation can enhance model robustness and generalization performance. Interpretability and explainability. Enhancing the interpretability and explainability of LLMs is essential for building trust and understanding in AI systems. Research efforts focus on developing techniques to interpret model predictions, visualize internal representations, and provide explanations for model decisions. Sustainability and environmental impact. Large-scale training of LLMs consumes significant computational resources and energy, raising concerns about the environmental impact of AI research and development. Sustainable AI initiatives aim to reduce the carbon footprint of training models through energy-efficient hardware, optimized algorithms, and renewable energy sources. Collaboration and knowledge sharing. Collaboration among researchers, practitioners, policymakers, and industry stakeholders is crucial for advancing the field of LLMs and addressing complex societal challenges. Knowledge-sharing platforms, open-source initiatives, and collaborative research efforts promote innovation, transparency, and responsible AI development. The course Introduction to Large Language Models offers a comprehensive exploration of the foundations, applications, and societal implications of large language models, LLMs, in natural language processing, NLP. Beginning with an overview of the fundamentals of language modeling and the architecture of LLMs, the course delves into the training techniques, evaluation metrics, and fine-tuning strategies employed in building and optimizing these powerful models. Students engage in hands-on projects and exercises to gain practical experience in building and fine-tuning LLMs for specific NLP tasks, fostering a deeper understanding of transfer learning and customization techniques. The course highlights the diverse applications of LLMs, ranging from text generation and translation to question answering and chatbots. Through case studies and real-world examples, students explore how LLMs are revolutionizing various industries and domains, driving innovation and enhancing communication and accessibility. However, alongside their transformative potential, LLMs also raise ethical considerations and societal impact, including bias and fairness issues, privacy concerns, and the spread of misinformation. Through discussions and exercises, students grapple with these challenges and learn about mitigation strategies and responsible AI practices to address them. Looking to the future, the course explores emerging trends and advancements in LLM research, such as scaling models to larger sizes, integrating multimodal understanding, and enabling lifelong learning capabilities. While LLMs hold immense promise for advancing NLP and AI, addressing open challenges such as bias mitigation, model robustness, and environmental sustainability requires collaborative efforts and ethical governance. By upholding principles of fairness, transparency, and accountability, stakeholders can harness the full potential of LLMs to benefit society while mitigating potential risks and ensuring equitable access to AI technologies. In conclusion, the course Introduction to Large Language Models provides students with a holistic understanding of the capabilities, challenges, and societal implications of LLMs in natural language processing. Through a combination of theoretical lectures, hands-on projects, and discussions, students acquire the knowledge and skills necessary to navigate the complex landscape of LLMs responsibly and ethically. As we reflect on the journey through this course, it becomes evident that LLMs represent a transformative advancement in NLP, with far-reaching implications for communication, innovation, and accessibility. From generating coherent text and facilitating language translation to powering virtual assistants and chatbots, LLMs have become indispensable tools across various domains and industries. However, amidst the excitement surrounding LLMs, it is crucial to acknowledge and address the ethical considerations and societal impact they entail. Bias and fairness issues, privacy concerns, and the spread of misinformation underscore the need for responsible AI practices and ethical governance. By promoting transparency, accountability, and inclusivity in the development and deployment of LLMs, we can ensure that these technologies benefit society as a whole while minimizing potential risks and harms. Looking ahead, the future of LLMs holds immense promise, with ongoing research and advancements pushing the boundaries of what is possible in NLP. By embracing collaboration, innovation, and ethical principles, we can harness the full potential of LLMs to create a more inclusive, equitable, and sustainable future for humanity. As students embark on their journey beyond this course, they carry with them the knowledge and responsibility to shape the future of AI in ways that prioritize the well-being and interests of individuals and communities worldwide.